Good afternoon, everyone. Let us start the second week of this Bootstrap conference. And today we have Shai with his third lecture. So, you know the style, if you want to interrupt, he's very happy that you just step in. Please, Shai.
Okay, great. So thanks for having me again. So this is the third in a series of 4 lectures. This one will be talking about bootstrapping correlators of operators with global symmetries, and is based on the 6th section of the online notes. Great, so let's jump right in. So an overview of this lecture. So first we're going to discuss correlation functions for operators transforming under global symmetries. Then we're going to discuss how to derive the crossing equations for 4-point functions of operators with global symmetries. In particular, we're going to give a worked example for the case of fundamentals of ON. Then we're going to describe how to compute this input for SDBB in practice, again using screen shares. Then we're going to discuss how to run SDBB, and then we're going to introduce a new numerical method called hot starting. So this is actually not in the lecture notes, but will be in the lecture. And then finally, we're going to discuss comparing the Bootstrap results for this ON Bootstrap to Monte Carlo, as well as large N calculations for the critical ON vector model, just to see that it really works. And as always, there will be some problem sets accompanying this lecture, which will allow you to reproduce all these results yourself. Okay, so let's talk about some basics for kinematics of 2- and 3-point functions. So we start with the 2-point function. So we consider a spin L complex operator O with these 3 labels, delta for scaling dimension, L for spin, and R for representation under some abstract group G, which we only ask that it be compact, with index A. So the first thing we want to do is define a reality condition, because now that our operators can be complex. And so as usual, you want a reality condition such that if you act with, if you conjugate twice, you should go back to the original operator up to some invariant tensor, delta AB. So we normalize the operator O to have unit 2-point function that respects the reality condition as well as the reflection positivity requirement, such that the 2-point function be positive. So one simple choice, which is the choice we're going to make, is to give the following normalization of the 2-point function. So you see that it looks exactly the same as the 2-point function when you didn't have any global symmetry indices, except now you have this invariant tensor delta AB bar, which is appearing here. So I should note that when the representation is real, then usually you can just choose this invariant tensor just to be a Kronecker delta, as it looks like. But when the representation is complex, there can be cases when it's more non-trivial. So sometimes maybe it'll actually be an epsilon tensor, for instance. So it's not always just a Kronecker delta. Okay, but this is just completely decided by the reality condition, so that's not something you have to choose. Okay, so now let's talk about the various OPs and 3-point functions we can build up using complex operators in representations of a global symmetry group. So we consider a complex scalar phi in representation fancy R of G, where now I is actually an index, so it's not just a label. And we're firstly going to consider the OBE between phi and phi bar, where in principle they can have different indices I or J bar. And this is going to include operators O, whose representations R are in the tensor product of fancy R with fancy R bar. And so because we are doing the OP of the operator with its complex conjugate, this implies that the operators that appear in the tensor product must be either real or come in complex conjugate pairs. So in the case of this OPE, the 3-point function is as follows. So we have phi, phi bar, and O. And then we get the usual space-time dependence, which is the same as the case with no global symmetry. We also get an OP coefficient, as usual. We also get these Z's, which are also just the space-time dependent factors. And the only novel ingredient is that we have this tensor structure T bold, which, as expected, includes all the various global symmetry indices. So we have the index I for phi, the index J bar for phi bar. We have the abstract index A for the operator O, which is in some representation R, and then we label the tensor structure by that representation R. So if the representation is real, then we could choose these tensor structures such that the OP coefficient is real as long as the spin is even. Alternatively, if the spin is odd, then we can choose them to be pure imaginary. The other possibility is that if R comes in complex conjugate pairs, then we can choose the tensor structure for each of these pairs. So you have TR bar, such that the OP coefficient themselves will come in complex conjugate pairs. Okay, so very simple. Now we could talk about the other OPE we can take. So we just spoke about the phi bar OPE. Of course, you can also take the phi OPE. So in this case, you include operators O with representations that now appear in the tensor product fancy R with fancy R. So it's not fancy R bar. And so these representations, unlike the previous case, are now generically going to be complex, such that their conjugate representations will alternatively appear in the OPE phi bar. So because we now have the OPE as well as its conjugate, we should show the 3-point function for the OPE as well as its conjugate. So on the top line, we have the phi 3-point function, which includes this tensor structure Tija, labeled by representation R. And then on the second line, we have the conjugate 3-point function, now with phi bar, as well as O bar, which basically looks exactly the same, except we now have the conjugate tensor structure as well as the conjugate OP coefficient, where we can choose these 3-point tensor structures such that the OP coefficients themselves are conjugates of each other. Another novelty we have now that we're doing an OPE between two identical operators is that if R is in the symmetric/antisymmetric product of this tensor product, then the corresponding 3-point tensor structure will be either symmetric or antisymmetric. So it's symmetric in the symmetric case, antisymmetric in the antisymmetric case of the indices I and J, which then implies that the spin must be even in the symmetric case or odd in the antisymmetric case. So this is kind of the global symmetry analog of what we discussed in the earlier lectures when you had a 4-point function of identical real scalars, such that exchanging the first and second operator required the spin be even. So now this is kind of the analogous case where if it's the symmetric representation, the spin has to be even. If it's the anti-symmetric representation, the spin has to be odd. And the reason why you have one or the other is simply because exchanging these labels now will change this tensor structure up to a sign, depending on whether or not it's symmetric or anti-symmetric. Okay, so so this is the main difference in terms of kinematics. So let me know if there's any questions. Otherwise, I will move on. Okay, so the obvious question is, how do you compute these tensor structures? So we will start by considering the case of continuous symmetries, which is the case most often encountered. And in that case, we can compute each tensor structure by using the quadratic Casimir for the group G. So this is just one way of computing it. I'm sure there's other ways, but this is the way I personally find simplest. And it's very general. It works for pretty much any case. So first, I'm going to give an abstract description of how to compute these tensor structures, and then I'm going to give a practical example in case the abstract description is too abstract. So we start by expressing these abstract indices I, J bar, and A as collections of fundamental or anti-fundamental indices I of the group G, such that this 3-point tensor structure can be totally written in terms of either fundamental or anti-fundamental indices. So just to recapitulate, so the original indices I, J, bar, and A, these are just abstract indices. So you can imagine any representation and you just give one index for that representation. But because we want to do practical calculations, we want to deal with the simplest kind of index, which is the fundamental index or the anti-fundamental. So that's the first step. Second step then is that you consider a basis of all tensor structures, fancy B, which have the same number of these fundamental or anti-fundamental indices as the 3-point tensor structure. And then you construct the quadratic Casimir C by squaring generators, which will be in the product or rep formed by all these indices. And so this is why we're just using fundamental indices, just to make everything very explicit, because it's very easy to find explicit formulas for what generators are. You can just Google it, written in terms of fundamental and anti-fundamental indices for pretty much any continuous group you would care about. Then you can act with the quadratic Casimir C on the I and J bar collection of indices for each of these, for each of our basis B. Where note that we were only going to act on the I and J type indices. We don't act on the A indices. So we leave those free. So in particular, the equation is that this quadratic Casimir acting on one of these basis elements B is going to give you some linear combination of the basis elements with various coefficients. You then take the eigenfunction of this system, and each eigenvalue will then correspond to a different tensor structure, where the tensor structure will then be an eigenfunction. And you know which eigenfunction corresponds to which representation because the eigenvalue corresponds to the what's called the quadratic Casimir value, which is just like a standard number in group theory. So like if you go online, you can find tables of quadratic Casimir numbers for pretty much any representation in any group. You can even find a formula for like very general groups. And so you just assign that number to their representation, and then that will tell you which eigenfunction is which. So in case this is too abstract, we will show an explicit example in a moment for fundamentals of ON. And also in the lecture, also in the assignment for this lecture, there's another example for SUN. I should also note that this method I described is for continuous symmetry groups, in which case you have a quadratic Casimir. Of course, for discrete symmetry groups, you don't. In that case, there's a different canonical way of computing these three-point tensor structures, which was introduced in my paper with these authors. I mean, morally, it's very similar. You're also just constructing projectors. It's just in the case of a discrete symmetry, you do it using character tables instead of using the quadratic Casimir. Okay, so any question about this method? Okay, good. So that was discussing how to construct three-point tensor structures. So now we can move on from 2- and 3-point functions to 4-point functions. So to compute the 4-point function, as usual, we take the OBE twice. The novelty in the case of operators which have this global symmetry representation, and in particular complex operators, is that remember there's different OPs we can take. You know, either we have phi and phi or we have phi and phi bar. So let's start with the case where we take the OPE of phi and phi bar twice. Because of course the whole 4-point function itself has to be a singlet. So you always need 2 phis and 2 phi bars. Okay, so we take the OP of phi and phi bar twice. So that gives us this OP coefficient squared. Notice the OP coefficient is phi and phi bar because that's the OP we took. And then we just get the usual space-time structure, the same thing we got in previous lectures. The novelty is that now when we're summing over operators, they're labeled not just by dimension and spin, but also by the representation that can appear in this tensor product. And then of course, there's a 4-point tensor structure for each representation. Note that the conformal block itself does not depend on the representation, because it only depends on the conformal group. So like the difference between operators and different representations is completely this tensor structure. Of course, there's a different OP we can take. Instead of doing phi and phi bar, you could just do phi and phi, and then additionally phi bar with phi bar. So when you take this OP, so now you're just going to get different operators in your tensor product. So now, because now you're looking at the tensor product with fancy R and fancy R, not with fancy R bar. And so you get a different 4-point tensor structure, and correspondingly, you also get different OP coefficients. So now it's lambda phi phi, and then multiplied by lambda phi bar phi bar. Where recall that if the spin can only be even or odd, depending if R is in the symmetric or anti-symmetric product of fancy R with fancy R. So finally, we need to identify how to compute these 4-point tensor structures. But that's very simple. You can do it simply by just contracting the 3-point tensor structures we just computed. It's actually very important that the one comes from the other because, of course, we have this OP coefficient which is appearing in 2 places, in the 3-point function and the 4-point function. And we want these definitions to be consistent. And this will be especially important, if you one day deal with Bootstrap systems with many correlators and you have all kinds of mixed correlators, you want to make sure you're dealing with the same consistent OP coefficients. So that's why it's very important to make sure that all your OP coefficients are defined consistently. And that means you have to make sure to define your tensor structures consistently. This was partly the motivation for why we chose the specific normalization of conformal blocks and 2- and 3-point functions we've been using throughout these notes. This is just to make sure that the identification is very simple, because other choices would lead to extra factors in identifying the 4-point and 3-point tensor structures. Okay, so let's give an example of a notable operator that appears now that we have a global symmetry transformation. So recall that all local CFTs had a stress tensor, which had spacetime dimension 2 and spin 2, and it always occurs in the singlet of the global symmetry group. But now there's another conserved current we can have, where whenever we have a continuous global symmetry, we have a conserved current which has dimension d-1 and spin 1, and this by definition occurs in the adjoint of the group G. So this is another operator which is guaranteed to appear. Which is pretty rare, because if we're working with some system without any supersymmetry, a priori, we don't really know anything about the spectrum, aside from the fact that there's the identity and that there's these conserved currents. So these are very, very valuable operators. So the same way that in the case of the stress tensor, we had a conformal word identity that related its OP coefficient to a certain quantity, which was defined as the coefficient of the canonically normalized two-point function. So there's an analogous relationship now for the global symmetry current. Recall that we always unit normalize our two-point functions, which is the normalization given on the previous slides. But there is a different normalization of a two-point function, what is called the canonical normalization. And when you normalize the two-point function canonically, then its two-point function would have a coefficient, what I call Cj, which depends on the theory. Now, for us bootstrappers, we always normalize everything with unit two-point function. And so thus, this coefficient Cj, which would have appeared in the two-point function, instead is now pushed into the three-point function. So i.e., it is related to the OP coefficient. So in particular, if you work out this algebra from the conformal word identity, you will find that the OP coefficient is related simply to the inverse of the square root of this coefficient Cj, where this is with the choice of a tensor structure in the three-point function b minus I, g, a, I, j, where g is the generator of the group. So recall this is the adjoint representation, thus it makes sense to choose our tensor structure just to be the generator, which is in the adjoint. So one thing I should note is that if you're talking about a non-local CFT, such as a generalized field theory, then the same way it didn't have a stress tensor, it will also not have a global symmetry current. So you don't have to have these global symmetry currents. It's only if you have a local CFT. Also, even if you have a local CFT, if the group G is a discrete group, then there will also not be a global symmetry current. So this is something you only have for continuous symmetry. Just as a technical comment, you might recall that for the stress tensor, when we related the OP coefficient to this coefficient CT in that case, first of all, the coefficient involved certain numbers, but that was a choice. But one thing which wasn't a choice is that delta phi itself appeared in this relationship, whereas for CJ, it does not appear. And so that is kind of an important practical difference between the stress tensor and the global symmetry current case. Okay, so now let's discuss the crossing equations that we get in the case of global symmetry. So as usual, we can take the four-point function and we can add it to a version where we swap 1 with 3. In this case, we also have to swap the corresponding global symmetry indices. Then we can relabel 1 with k, I with k, and this gives us two kinds of crossing equations. So the first crossing equation is the one you got from looking at a configuration which looks like phi, phi bar, phi, phi bar, and then you switch 1 and 3, you still have phi, phi bar, phi, phi bar. And that's why you have the same representations in both the original configuration and its swapped version. And then in principle, we could either add or subtract these two f functions, where recall that the f functions are just combinations of conformal blocks defined here. The second kind of crossing equation is where we started with the configuration phi, phi, phi bar, and then upon switching 1 with 3, then we got phi bar, phi, and phi, phi bar. And so that now includes different representations, because it includes representations in the fancy R bar. And so the second crossing equation is a little more complicated than the first one. And again, there's always the choice of either adding or subtracting the blocks, which gives you either f plus or f minus, as defined here. Okay. So a little more about these crossing equations. So the first step is that we just write down crossing equations in terms of these f's. But here, notice in the crossing equations, these four-point tensor structures are still appearing. Whereas at the end of the day, we want to get some kind of crossing equation which literally just involves these f's times their appropriate OP coefficients without these tensor structures. So we do that simply by just solving for the f's, because these four-point tensor structures are just tensor structures, so you can just solve for every single entry. And at the end of the day, this is going to give you some vector of f's multiplied by OP coefficient summed over all the operators in the OP. So this v is some linear combination of the f's, and the length of v is the number of tensor structures that appear in the four-point function. And so it's important to emphasize that this is the number of tensor structures, not the number of representations, because those in principle can be different. So for instance, we assumed here that representations do not appear twice with the same spin in a given OPE. Because if that were to happen, then you would have multiple tensor structures for just one representation. And that means you would in general have to deal with matrix constraints in order to implement this with the conformal bootstrap. But we're not talking about matrix constraints in this lecture. We'll be discussing that in the next lecture. So for now, we're going to assume for simplicity that each OPE with a given spin only appears once. But it's important to note that this is just a special case. The more general case, you would actually have to have matrix constraints. Okay, so any questions about these crossing equations? Good. So hopefully everybody is following. Okay, so this has all been very abstract so far. So now let's give an explicit example, which is fundamentals of the ON group. So we will consider an operator phi. It's a real operator, and it's in the fundamental representation of the group ON with index I. So in this case, when you look at the tensor product, it's going to include three representations: the singlet S, the antisymmetric A, and the traceless symmetric T. Where the singlet is in the symmetric product, the antisymmetric is in the antisymmetric product, and the traceless symmetric is also in the symmetric product. And so this means that you only have even spins for the singlet and the symmetric, and you only have odd spins for the antisymmetric. I also should note that in this case, the adjoint representation is the antisymmetric representation. So that is the representation where we expect the conserved current to appear. So the first step we do is we want to compute the 3-point function tensor structure. And so we do this by using the method introduced in the previous slides, which is that we're going to parameterize all our indices by fundamentals. So this case is especially simple because in this case, our I and j indices just are fundamental indices because we're just looking at the fundamental representation, which is why I chose this example because it's so easy. So in this example, the only index which we have to parameterize with fundamentals is already the index A, which so far is just the abstract index for each of these three representations, S, A, and T. So we're going to choose to parameterize this A with two fundamental indices, K and L. And so that means we can choose our basis of tensor structures to be the following three tensor structures. So it's just every combination of I, J, K, and L as written in terms of these Kronecker deltas. So the next step is that we want to define our quadratic Casimir as written with these indices. So here we take our generator G, which is defined explicitly here in terms of Kronecker deltas, and we square it, which is the definition of a quadratic Casimir. And so notice that we are defining the quadratic Casimir, which acts on the indices I and J, and the indices KL are left as free indices, because that is our general method, which is that the quadratic Casimir always acts on the I and J type indices, and it doesn't act on the A type indices. We can then look in some textbook, and we will learn that the eigenvalues for the singlet, the antisymmetric, and the traceless representation for the group ON are 0, 2n minus 4, and n. And so then we act with this quadratic Casimir on this basis, and we solve the resulting system. We compute its eigenvalues and eigenfunctions, and we find the following eigenfunctions with eigenvalues corresponding to these representations. So for the singlet, we get this following eigenfunction, which is just the first element of basis. For the antisymmetric, we get the difference between two elements, and then for the traceless symmetric, we get all three of them with certain coefficients. So I should note that the overall coefficients that I've chosen in my eigenfunctions at this point, of course, are arbitrary, as is always the case for eigenfunctions. But you'll see in a moment why we chose the specific coefficients that we chose, including these signs. So for instance, one choice is already immediate, which is that remember that there's a privileged choice of 3-point tensor structure such that the OP coefficient of the conserved current is related to Cj in the canonical way. And that is the choice where its 3-point tensor structure is just minus I times the generator. And so that is exactly what we've chosen for this corresponding 3-point tensor structure. And so that's why we have this -1 and everything else. Okay. So next, we take our 3-point tensor structures and we simply square them to get the 4-point tensor structures. And so when we do that, we get the following 4-point tensor structures. And so now you can see why we chose the specific coefficients from the previous slide is that it gives us this particularly simple form. And this is also the form that's used in the literature. So I was trying to stay as simple as possible. So I should note that it doesn't actually really matter what the overall number is multiplying these tensor structures, aside from the fact that it has the right sign. Because the sign of the tensor structures will decide whether or not you have correctly normalized things such that the OP coefficient squared is positive. Because if it's not positive, then you're going to have trouble for the bootstrap. So in principle, if we define all our 4-point tensor structures in terms of 3-point tensor structures consistently, you don't have to worry about these signs. But it's always good to double check this, because when you're doing this in practice, there's a lot of room for error. And so what I find is the best way of double checking to make sure that you got your signs correct is just to compute the 4-point function in the free theory and expand in these tensor structures in blocks. And then you can see very explicitly whether or not you're getting positive OP coefficient squareds or not. So it's a fail-safe method. So let's see how this method works in this simple case. So here we take the 4-point function of phi in the fundamental. We compute it in the free theory just by doing Wick contractions, where phi is dimension half because we're doing 3D. So we get this is the following quantity. This is the 4-point function, the complete answer, where remember U and V are the conformal cross ratios. Then we expand U and V in terms of the variables R and eta, which remember were the natural variables that we expand conformal blocks in. And we can expand it to some low order. So let's say we expand it just to order R squared. So then we can write that in terms of these conformal blocks, and we can see what the coefficients are that are appearing. And so as you see, they are all positive, as we want. Now, I should clarify that the reason they're all positive, this was very related to the choice of global symmetry, the choice of conformal block normalization that we chose. So there are other normalizations in the literature where very perversely, they put in a factor of -1 to the spin. And then in that normalization, you actually want to see minus signs for odd spins. So this is something you have to be careful about. So this very much depends on your choice of conformal block normalization. And for these lecture notes, I've just chosen what I think is the simplest normalization, such that you just want to get positive signs everywhere. Great. And so this has been a very nice check. This kind of free theory type expansion can also be useful for checking other things, such as if you want to double check the way that OP coefficients are related to CJ and CT, well, you can just do it in the free theory, and then this will tell you what the explicit relation is. Because that's something that's true in any theory, in particular the free theory. Okay, so now that we've computed our tensor structures, we've checked that they have the correct signs. So now we can just compute the crossing equations as discussed abstractly before. And this leads to 3 crossing equations. Remember, we write our crossing equations as this vector V. And the fact that we got 3 of them was expected because we got 3 tensor structures. And so in this simple case, it actually turns out that the number of tensor structures was in 1-to-1 correspondence with the number of representations, but that didn't have to be the case. So the first thing you should note is that in these tensor structures, n is appearing explicitly in the crossing equation. And I should note that, in fact, this is the only place where n will appear. And so that means the only way you can tell the bootstrap that you're looking at, say, the O10 model instead of the O11 model is by putting in either 10 or 11 into this crossing equation. So there's no other part of the bootstrap where you put in the value of n. And because n appears as just a variable, that means in principle, if you're feeling adventurous, you could imagine not even putting in integer values of n, but putting in any value of n, say even a complex value of n. So I would be cautious about doing that though, because as Slava and Damon showed in a paper, when n is not an integer, then you don't have a unitary CFT, at least in most cases. Although still, if you're feeling adventurous, there might be some cases where you could maybe let n be very close to integer, such that the lack of unitarity would be very small. Okay. So just to also emphasize this fact that we found 3 crossing equations with the same number of 4-point tensor structures, I just want to emphasize that this was only in this special case. So an example of another case where this wouldn't be true is that if you would have had complex conjugate representations appearing, then those only count as 1 structure. So even though you're getting 2 representations, it just counts as 1 structure, and so it only leads to 1 crossing equation. And then similarly, if you have the same representation, which would appear twice with the same spin, then that would have actually given you several 4-point tensor structures, and then that would have led to multiple crossing equations. And so the story in general is more complicated for the counting of crossing equations, although it always scales in general with the number of representations. Okay, so this concludes our explicit example of the fundamentals of ON, which is probably the simplest case you can find. A slight variation of this is the case of U1. And this allows us to talk about complex operators, whereas before we were just talking about real operators. So now we let phi be a complex operator in the charge representation 1 of U1. And so notice that there's no labels because we're just saying it's either charged or uncharged. So because we have a complex operator, now there's different OPs we can consider. So we can consider R with R bar, and that OPE includes the even spin charge 0 representation, as well as the odd spin charge 0 representation, while the other OP, R with R, includes the charge 2 representation, which is in the symmetric product, so it only has even spins. So there are no indices in this case, but the sign of the structure for each R is still non-trivial. And so that's what I wanted to emphasize with this example. So like, you might think like, oh, there's no indices, who cares? I'll just normalize them all to 1. If you did that, you would get the wrong answer and the bootstrap wouldn't work. So it's very important that you choose the signs correctly. So for instance, for 3-point functions, I'm going to choose the signs for the even spin singlet and the charge 2 to be 1. And for the odd spin singlet, I'm going to choose it to be -I, where this -I is motivated, as usual, by our desire to match the canonical normalization for the current. Because remember that it should always be -I times the generator. Or I think it's I times the generator. Okay, so now for the 4 points, we then just square these 3-point tensor structures. So in this case, it's just trivially 1. But the non-trivial thing is now for this odd spin singlet, now we get -1. And so this minus sign is very important. If you had been cavalier about it, you would have gotten the wrong answer. So that's what I'm trying to emphasize with this example. Okay, so now that we have our tensor structures, we work out the crossing equations. Because phi is complex, that means we're going to have to use both kinds of crossing equations. So remember, in previous slides, we discussed how for a general complex operator, there's like 2 kinds of crossing equations. One which includes both R OP, the other one which include R bar. And so now we're going to get both kinds. So the first kind just gives one crossing equation, which is the crossing equation of phi bar, phi bar. And this includes just the representations of the singlet with either even or odd spin. And the second one, which is phi bar, upon crossing, that also gave you phi bar. And that, in this case, we get 2 kinds of crossing equations, one where we add them, one where we subtract them. So now we can try to see how these are related to ON, because of course, U1 is just isomorphic to SO2. And specifically for the 4-point function of fundamentals, there's no difference between SON and ON. So SO2 should just be the same thing as O2. So we should get the exact same crossing equations. And so you will notice that you do get the exact same crossing equations, provided that you normalize your tensor structures as follows. So this is basically the same normalization as the previous slide, except instead of letting this charge 2 normalization be 1, we let it be 1/2, just so that we can get the exact same cross equation as ON. Although remember that it doesn't really matter what the overall number is aside from the sign, because the overall number is just some choice of normalization, and you can always just change that arbitrarily. So, but the important lesson is just that, as expected, you get the same cross equations for U1 as well as O2. Okay, so now that we have discussed this kind of general introduction, we can now discuss how to implement this with SDP. And so this is basically the same thing as the case without global symmetry, except with 2 simple changes. So firstly, the polynomial constraints that we enter will now have 2 new labels. So first of all, there's a label beta, which is the label for each crossing equation. So for instance, for the ON case, we have 3 crossing equations, so beta goes from 1 to 3. And then also, we have the polynomials are labeled not just by the spin L, but also by the representation R, because there's multiple representations that can appear, which in this case, there's also 3 of them: singlet, anti-symmetric, and traceless symmetric. Another change is that the functional, instead of being labeled just by M and N for the Z and Z bar derivatives, is also labeled by beta for the number of crossing equations. So you could ask a question of, now that I have these extra labels, do I expect that it will be easier or harder to find a functional? Correspondingly, will I get a bigger or smaller allowed region? So whenever you increase the space of functionals, which we are increasing because we now have a label beta, this makes it easier to find an alpha which satisfies, for instance, the scaling dimension algorithm, which would make the disallowed region bigger. On the other hand, though, we now have extra constraints because now we have polynomials not just for every spin, but also for every representation R. And that in general makes it harder to find an alpha. So we have these kind of 2 competing principles, and this is why it's not obvious, a priori, like that adding a certain global symmetry representation will like make your bounds better or worse. Now, of course, on like, on intuitive level, you would expect that like putting in more constraints should make the bootstrap more constraining. But I'm just saying that it's not immediately obvious just by counting, the size of the functional space versus the size of the constraints. Okay, so now I will share my screen in order to demonstrate how to implement this in practice. Okay, so I will share my Mathematica screen. Okay, great. So hopefully you guys can see the screen. And I will go up to the section where we describe this implementation, and I will describe it for the example of the ON model, and I will do that both for the scaling dimension algorithm as well as the OP coefficient algorithm. So first we're discussing the scaling dimension algorithm. And so this should be familiar from previous lectures, also if you did the problem sets. So the first step is that we have some function which loads in conformal blocks. We're still looking at operators which have the same scaling dimension, so nothing has changed there. The first thing that changes is that whereas in the previous lectures we just had one set of polynomial constraints, what we called V, now we have different polynomial constraints for each representation. So for instance, in the singlet representation, here we have this list of constraints where also there's 3 crossing equations. So we have 3 lines here instead of just being 1. And the specific values we get here are exactly what appeared in the lecture notes. So we get 0, 1, and 1. We'll also note that we now remember there's 2 definitions of f. There's f plus and f minus, because in one case we add the block from its swapped version, in another case we subtract. And so now that we have global symmetry, in general, both can appear. Whereas previously in the case of just an identical correlator with no global symmetry representation, we only ever had f odd. Okay, so that's another change. And so here for the singlet representation, we go over all even spins. Then we have the symmetric representation. We also go only over even spins, but now there's different coefficients for the 3 kinds of cross equations. And notice here, this is where n is appearing, very importantly. Finally, we have the anti-symmetric representation, where now we go over all odd spins. And again, there's just different numbers that appear in these 3 crossing equations. Okay, so then we put in these 3 entries into our polynomial constraints. We now have the possibility of doing scaling dimension bounds on operators in each representation. So we could choose either the singlet, the traceless symmetric. These are the ones that have a scalar. In principle, we could also do the anti-symmetric, but in that case, we'd have to start at spin 1. Now for the unit vector, we input it in a similar way as the single correlator case, except we have to recall that the unit vector is in the singlet representation. So the 3 crossing equations that appear should correspond to the precise crossing equations that appeared in the singlet. So in particular, notice that in the singlet, we have 0, 1, and 1. And that's why here we have 0 times this, and then just the odd derivatives, and then the even derivatives. Okay, so that's it. Those are the only changes. Everything else is the same. And so then you just produce the file by doing Shift-Enter, and you run it with SDBB, and the output will look exactly the same. So that I don't think there's any reason to go over that again. The other case we can discuss is doing, well, okay, I mean, I guess it's also basically the same. So I think we will skip that. Okay, great. So this concludes our discussion of how to implement global symmetry. So now I will share screen back with my lecture notes. Share screen. Great. Okay, great. So the next thing I'm going to discuss is a method called hot starting. So SDP slows down as the number of crossing equations increase. And so in this lecture, we've just discussed how now that you have global symmetry representations, you can have many crossing equations. So if the ON model is just 3, it's not so many. But once you go to more sophisticated examples of Bootstrap, you can have many, many crossing equations. Like, for instance, in like a recent study of the O3 model, we had something like 28 crossing equations. And so once you have so many crossing equations, the Bootstrap is going to go very, very slow because these functionals have many labels. And so we want to develop some kind of method to speed it up. And the easiest method that I know of is this thing called hot starting, which was suggested many years ago, but first actually implemented in practice by this paper by Yuji Tachikawa and his student Go a year ago. So let's discuss how this works. So recall from the previous lecture that SCBB starts by choosing some default value of these variables, capital Y and Y, as well as their dual version. And then it gradually changes these values to get to a point that is either dual or primal feasible. And then in the case of the OP coefficient algorithm, eventually you want it to be optimal, such that you have an objective function for both, which gets very close to each other. And so when we originally discussed this SCBB implementation, the choice of the default Ys was, in a sense, kind of generic, in the sense, so it wasn't specialized to each scenario. We were just basically choosing like an identity matrix times some convenient number. But that's like a little bit stupid, because if we are going to be running many points with the Bootstrap, which is what we want to do in practice, for instance, if we want to get some nice plot where we see a kink, we might want to run the Bootstrap at like 50 different points. And so instead of just choosing the same default value to start this algorithm every single time, why don't we try to use a first value which is closer to where we want to end up? So it's like very close to finding an optimal point, or very close to finding either a dual or primal feasible point. And so this is basically what hot starting is. And so the name is descriptive, which is that like if you're cooking, instead of like every single time you make a new dish having to turn on the oven, you can just keep the oven on and then all your dishes will cook quicker. So that's what hot starting is. One thing you have to be careful when you're hot starting is you want to avoid numerical instabilities. And so one nefarious thing that can show up is, remember we discussed in previous lectures how there's like a certain foolish definition of scalar blocks such that when the spin is bigger than 0 for identical correlators, the polynomials don't have a constant term. And so this leads to some numerical instabilities. And this is why when I was discussing the implementation, I was always dividing by x such that there is a constant term. So that's an example of something you have to do to make sure that hot starting works. Otherwise, the instability ruins it. An alternative method you can do, which is a bit more general, is that you can always put a very small gap for all operators in all sectors. So this is called the twist gap because you put it on every single spin and you just make it so that the gap, instead of being unitarity bound, is like unitarity bound plus 10 to the minus 5. And this will usually get rid of all these stupid instabilities. But also it's something which is totally reasonable because like unless you're looking at a conserved current, you wouldn't expect there to be an operator which is like 10 to the minus 5 away from unitarity. Okay.
Can I ask a question? Because why? So is this 10 to the minus 5 gap, is it kind of, is it equivalent to dividing by that x? Is it just because we don't want to divide by x we put this gap, or is there any other reason?
Okay, so
I'd be surprised. I mean, what is so
yes,
special about this conserved currents at the conservation as opposed to like, why, for example, is there this instability close to conserved currents, but there's no this instability close to, I don't know, epsilon operator or sigma operator?
Okay, so I don't have a full answer for this. Maybe there's someone in the audience who does. I'm not sure if there is an answer to this. I think to some extent this is kind of just a rule of thumbs that people have discovered. I mean, in the case of like dividing by x, in that case it is clear because like, you know, like the fact that your polynomial constraint doesn't have a constant term is like a fake feature. It's like it should have a constant term. It's just that the poles that you were choosing to construct your blocks with was like the wrong set of poles, so to speak. And like it was including a pole, you know, such that, you know, there's no constant term. Whereas for conserved current, you basically, well, I mean, first of all, yes, I mean, conserved currents, like you expect there to be actually an operator at unitarity, which makes them special. I think like, okay, I'm not sure, but I think the problem is if you just have these no constant term for like many, many blocks, then it creates an instability. And I think it's okay just to have it for a couple blocks. So I don't think there's necessarily anything special about conserved currents. I think it's just because there's just one conserved current, it's okay just to have one entry, you know, with no constant term. Whereas if you had that, you know, for every case, then it would ruin the stability. But also, I mean, even with the conserved currents, I mean, you're like, we still divide out by this x, and so we still restore the constant term. Like, yeah, so
I didn't pay so much. Like when you explained it last time, I didn't fully appreciate this x because, you know, we know that if the external operators have equal dimensions, then this spin L conformal blocks, they just go to a constant, well, not a constant, but some finite answer at unitarity.
Yeah.
So I think if I like do everything correctly, I don't expect this.
Exactly.
X.
Yeah. Okay. So this is exactly why I was saying that this is a stupid problem. This is actually a problem I complained about, but I was told that it's not important enough. So I mean, the reason why this comes up is because the choice of, okay, so when you're doing the recursion relation for blocks, the recursion relation involves this like set of you know, poles that you get when doing the recursion. Like there's 3 families of poles, and so like the set of poles for identical correlators is a smaller set than the set of poles for mixed correlators. Yeah. But the way scalar blocks was implemented is that they just always choose the set of poles for the most general case with mixed correlators. And I guess the reason they chose that because it's most general, and so like, I don't know, you just want to have some canonical choice. You don't have to keep changing it each time. But it makes it a little bit annoying that because you are choosing a larger set of poles than you actually should be using, in particular, it includes some pole, which makes it so there's no constant.
Yeah, I understand.
Yeah, so it's just like a stupid thing, you know. Like,
So we
there's
should
nothing
suggest that this be corrected in scalar blocks, because this.
yeah, well, I did suggest it, but I got some resistance.
Okay, I'll try to suggest this.
Okay,
The
great.
resistance is because it's simple to check it afterwards, right? You can just check if the polynomial is 0 at each of the poles, and then polynomial.
Oh yeah, I mean, I think
okay,
the resistance, from what I recall, maybe some of the resistors are in the audience, is that people didn't want to have, like, you know, many different like definitions of what scalar blocks is doing for many different cases, because then it could lead to a headache where it'd be like hard to compare blocks in different scenarios. So they wanted to be like, okay, we always choose this set of poles. In some sense, it doesn't really matter, except for this case of instability where we kind of like annoyingly have to like multiply back by x. And so I think that's the argument. But I agree with you. I mean, I do think it would be nicer if you just didn't have to divide by this x. Okay. Yeah, I mean, it also creates issues for other applications. Okay. So now I will share my screen again to show how this works. So I will share screen now with the terminal. Or actually, sorry. Okay, let me first share screen with my Mathematica notebook. So just to show you all the steps. Are you looking at my Mathematica notebook now? Okay, hopefully you are.
Yeah.
Okay, great. Okay, so we are going to demonstrate hot starting for the simplest case of the icing model, you know, just because that's the case we've already discussed in detail. So in previous lectures, we had done the scaling dimension algorithm, fixing the value of delta sigma to be 0.52, and then we changed the value of delta epsilon to be either 1.4 or 1.5. One was an allowed point, one was a disallowed point. So now let's just imagine for fun, we wanted to look at the point 1.6, which we expect to also be disallowed. So the first step I'm going to do is I'm just going to create the input for 1.6, which as usual just takes a couple seconds. And then I also want to demonstrate this hot starting also for the OP coefficient algorithm. So here I'm also going to create an input value for the OP for extremizing stress tensor OP coefficient. And now, just because I want to have a different point, I'm going to do it for delta sigma equals 0.53 instead of 0.52, which is okay. So now I've generated these things. So now instead, I'm going to share screen with my terminal. Okay. So let me make sure I go to the right thing. So hopefully you guys can see my terminal. Hopefully you see things changing. So the first thing we do is that as usual, we have to do this PVM to SDP so that we have the right input file. So I'll do that for this input 16, as well as this other stress tensor OP coefficient value. So now that we've created our STPB input, now we can just run STPB on it. So first I'm going to do it for this scaling dimension algorithm. Okay, so this is the line you put in. So let me explain this in detail again. So a lot of it is similar to the original STPB implementation. So we run Docker, we access Walter's code on the cloud. So this is what this STPB is, Walter Laundry 2.4.0. Here we say how many cores we're using, which is 4. Here's the parameter file, which is I just called param.stpp.
Shai, there is some problem because I think you shared the screen and then you changed the window and we don't see as a result.
Okay. So I will stop sharing and then I will reshare, and hopefully this time it will work. Okay, so terminal share. Okay, so you see the terminal now?
Yeah.
Great. Okay, so I'm just describing this input line. So it's the exact same thing as the old input line. The only change now is that there's an extra argument here called initial checkpoint directory. And this is what hot starting is, because all hot starting is that whenever STPB ran, it was creating outputting the values of these Ys. And so after STPB has ran, you have like the final Y, and we want to choose that final Y when running STPB again for some nearby point, because that will make things faster. And so what we're doing with this initial checkpoint directory is we are loading in the value of Y from the previous run. So when you ran STPB last time, in the folder where you were running it, there's an output folder which has the exact same name as what you ran. So it's like, because we ran input 15, the output folder was called input15.ck, which stands for checkpoint. And so this is just generated in that folder. And so that is the checkpoint directory. So that's the thing we're using to hot start. And then the actual value we're looking at is input 16, which is the value 1.6. Okay, so now let's run this. And as you see, it's extremely quick. So here we wanted to find a disallowed point. And so when we were running this last time, it had to take like, I don't know, maybe 100 steps or something to find a disallowed point. But now that we hot started it, it just took 2 steps. So as you see, it's much, much, much quicker. And so for the icing model, it's kind of like, who cares? Because it took a few seconds anyways. But you can imagine that once you're looking at more complicated examples, this is really a life changer. Okay, so that demonstrates hot starting for the scaling dimension algorithm. We can also demonstrate it for the OP coefficient algorithm. So now, as you see from this input line, we are loading the checkpoint of input CT, which was when we ran the OP coefficient algorithm last week, which had 1 value of delta phi. And now we're running it for a different value of delta phi, which is the input file input CT2. And so the goal is that this should go much quicker and that we should find our optimal value way quicker. Okay, so now we run this. Also, of course, we're using a different parameter file because we're doing OP coefficient algorithm. And so now we run this. And you might recall that last time it took something like 250 steps, and it took us like a couple minutes to get this optimal point. And remember, to get to the optimal point, like P obs and D obs, they started at like huge values. So like D obs was like 10 to the 35, and it took forever for it to fluctuate and eventually get down to a small number. Now everything is super quick because now P obs and D obs, they already start at almost the right answer because we expect the right answer to be like negative something slightly bigger than 1. And so they started very close to the right answer. So as a result, it only took like 43 steps to find our optimal solution. And so, this also works great. Cool. Okay, so this is our demonstration of hot starting. Now I will share screen back with the lecture notes.
Can I ask you a question?
Sure. Yeah.
And in the algorithm, we use the initial matrix scale to be something on 10 to the 30. And here, what happens if we put them to 1? Is it?
You're saying for the input value of this like these y's, if we had just started with like a small matrix?
Because we see that here we start around 1. So what happens if we don't start, but we start with?
The thing is, like, it's a little bit complicated though, right? Because like, I mean, there's many different values you're looking at. So like these values that are starting at around 1, these are like the D obs and like the P obs. And so like the fact they're starting near 1 is because we chose, like, I mean, it's like the whole system was such that it started near 1. So like, I don't know if there's like an immediate relation between the fact that these Y's, had a certain overall magnitude and the fact that the D obs and the P obs have a certain magnitude. So I mean, what I mean to say is that if you were just to start with values of big Y and small y, such that they were multiplied by a small number, I don't think that would make things quicker. Because what's important is that like you're near the actual solution, like not that you just have a small number.
Okay, thank you.
There's a bit more to it, right? You have the algorithm that SDPB uses. Ideally starts from an initial matrix, capital X, and a matrix capital Y that is bigger in the positive semi-definite matrices sense than the final matrices X, the optimal ones X and Y. Because then you can do this so-called central path and follow it down to optimality.
Yeah.
So what happens if you start with too low a value of the initial matrix scales is that this path just gets stuck. You're basically on the boundary of the cone of semi-definite matrices, and your next point points outward, which sucks because you want to stay inside that cone, and then the algorithm gets stuck. What Shai just did, starting from optimality, a primal dual optimal solution and hot starting, might run into the same problem. There might be a problem there too, that you get stuck. And you could see that in Shai's the SDPB output of the run that Shai just did. You can see that beta was huge. There were some very weird steps going on at the beginning. So this could be a problem. You can get stuck, and the risk is much greater if you start from a primal dual optimal solution rather than just a feasible solution.
Yeah. So I actually spoke to Walter about this, and Walter seems surprised that hot starting works. And so I guess maybe maybe it's not completely understood why it works, but I mean, in practice it does work. Although you should be careful that sometimes
starting from a primal dual optimal solution or hot starting from a feasible solution. Those are two very different setups.
Yeah. Well, yeah. So he was actually more skeptical about the feasible case. Like for some reason, he thought the optimal case, there was a greater chance of it working, and he thought it was more difficult from the feasible perspective.
I think the
In that
theory
case,
of convex optimization or of this algorithm would say it's otherwise. It's exactly the opposite.
yeah. Okay. Yeah. Yeah. So I guess that's why you're saying there was big steps in the beginning. Yeah. Okay. So it's important to keep in mind that there might be some cases, maybe if you're looking at some weird system where hot starting might not work. And so, I mean, you don't have to use hot starting, but it's like an optional thing, which makes things way quicker. And and you might have to fine tune it. I don't know, maybe increase the precision or something in case there's instabilities. Okay. So that's the hot starting demonstration. And so now we will conclude with some results for the ON model, comparing it between the Bootstrap results and previous results. So let's briefly review some previous results. So Monte Carlo lattice methods had been used to compute the scaling dimensions of the vector scalar operator, as well as the singlet scalar operator of the lowest dimension for the case n equals 2 and 3. So the vector is, of course, this what we're calling phi. So this is the external operator because it transforms in the fundamental. And so these are the predictions that Monte Carlo had to many digits. For the case of the traceless symmetric representation, Monte Carlo did not compute it purely from lattice. Instead, they used something called the pseudo epsilon expansion, which is like some weird combination of epsilon expansion plus other things. This is for the case n equals 2 and 3. And this method is not as good as just regular Monte Carlo, and that's why they only got a few digits of precision. People also computed the scaling dimensions in a large N expansion many years ago. And so, for instance, you can look at the case n equals 10, which is a big enough value of n, and then you get these approximate values. We're notice here that I can't put error bars because this is an asymptotic expansion, so in principle, it's just magic. Okay, so now let's see the results we get from the conformal bootstrap. So recall that we have multiple symmetry representations, so we can look at the bounds for each sector. So we're first going to look at the singlet sector. We'll look at the spin 0 operator. We have these dashed lines as well as the solid lines. The dashed lines are just with lower lambda, because this will be easier for people to reproduce on their laptop. Solid lines are with higher lambda. So these dots correspond to the Monte Carlo values for n equals 2 and 3, whereas for n equals 10, it's the large N value, which I put in gray. And as you see, there's a very clear kink in the plots right near these values predicted by these other methods. So I should just emphasize yet again that the bootstrap in principle is looking at any CFT which has a fundamental in the ON. So it wasn't just looking at the critical ON vector model. So in a sense, it's kind of a miracle that the actual critical ON vector model appears at such a magical point, at this kink, implying that it's appearing right at the boundary of this allowed region. And so this is the same thing which happened for the Ising model, which you can think of as the n equals 1 case. But now we see that it generalizes to all n. In fact, it even seems that the kink is getting clearer as n is getting bigger. Also note another fun thing, which was also mentioned in the previous lecture, which is that we see that as you increase lambda, in general, the plot changes a lot, but right near where the actual theory lives, it changes very little, which seems to be some principle to help you find physical CFTs, perhaps. Okay, so this is the case of the ON singlet bounds. One last thing to notice is that as n gets bigger, the bounds include the other bounds, which is perhaps what you might expect. Okay, so now this is for the traceless symmetric upper bounds. And so we also do this for n equals 2, 3, and 10. Again, we compare it to these other predictions. There's also a kink in these plots, although it's a little bit harder to see, especially for low values, or I guess in this case, it's actually the big value event, it's harder to see. But nonetheless, there is a kink if you look carefully, and it matches the known values. So it's interesting, if you compare these two plots, you'll notice that in one plot, it went purple, red, blue. Another plot, it went blue, red, purple. And so we can kind of explain what's going on there. So in general, because ON is a subgroup of ON plus 1, that means we expect that the bounds should get stronger as n would increase, because we're putting in a more restrictive symmetry group. And so for the traceless symmetric bounds, we see this very explicitly, which is that the purple line is below the red line, which is below the blue line. These are all upper bounds. That means it's getting more and more restrictive. But the singlet bounds seem to have the opposite pattern. We're notice here that the blue bound seemed more constricting than the red bound and the purple bound. And so is this a problem? I mean, they seem to break our intuition about the fact that ON plus 1 should be more constricting than ON. So the solution is that you have to be very careful about how you define your representations in ON versus ON plus 1. So in particular, a traceless symmetric operator in ON plus 1 contains a singlet operator under its ON subgroup, which generically has a smaller scaling dimension than the ON plus 1 singlet, which we can see from comparing the two plots. Thus, the only thing we should expect is that the value of delta t for ON plus 1 is smaller than the value of delta s for ON, and that is indeed the case. So basically, you just have to be careful that like there are more singlets from the ON perspective when you started from ON plus 1. And so that's why you shouldn't, so for the singlet plot, you shouldn't be comparing the blue against the red, you're comparing the blue against either this red or that red. And when you do that, you will see that, you know, the bigger the value of n, the more restrictive it is. Okay, so any questions about these plots? Okay, good. So finally, I will conclude by noting that there is a code that exists called AutoBoot, which can actually be used to compute the cross-union equations for operators in pretty much any representation of any continuous or discrete global symmetry group, which was done in this wonderful paper by Yuji Tachikawa and his graduate student. And so this means that you shouldn't be afraid of computing cross-union equations for all kinds of crazy groups, which used to be a barrier to doing the Bootstrap, because that is not a barrier at all. It can just be done automatically for you using the code from this paper, and it even puts it into the right format. You then might ask the question of like, okay, well, why should I even learn how to derive cross-union equations if this paper can do it? The answer is that, I mean, first of all, it's good to understand how things work. And secondly, understand the precise normalizations of OP coefficients that you're using in case you want to like compare it to other methods. Having to use their choice, which is kind of weird, you might want to choose your own choice, which you'll have your own justification for. Okay, so I think that concludes this lecture, and I will post the relevant problem sets, which basically involve reproducing these ON plots after the lecture.
Thank you, Shai. So let's thank Shai for his beautiful lecture. Any questions? Please go ahead. Who wants to speak?
Hi, can I make a small comment about or a question about this last slide?
Sure.
I think that this code only for continuous continuous symmetries, it only has like n equals 1, 2, 3 implemented, right? And anything.
Oh yeah. So yeah, I guess yeah. So yeah. So from what I remember, they haven't like loaded all possible groups. But yeah, actually, I don't know. Maybe they've been updating it. So maybe at this point they have loaded more groups. Yeah. So it might not be able to do literally any symmetry group. But it can certainly do many. So for the case of discrete symmetries, I think it can literally do any group, because for the case of discrete symmetries, there's a software called GAP, which is very useful, which is developed by mathematicians, and it involves all the information you would ever want to know about any discrete symmetry group, and AutoBoot connects to GAP, and so that's why it can do any discrete symmetry group. And I should also add that luckily, the area of the Bootstrap which is most open to students doing interesting projects, I would say, is discrete symmetry groups, because there's all kinds of these crystallographic groups which are waiting for people to bootstrap. And so in that case, you don't have to do any cross-equation calculations yourself. But I agree that in the case of continuous symmetry groups, not all of them are loaded in, so some of them you might have to do yourself.
Thanks.
It might be actually problematic as far as some product groups are concerned. So it might be able to do this. It might be able to do easily simple groups, but not necessarily direct products.
Oh, you're saying like they didn't implement direct products?
Yeah, because there are tables. So the way their codes work is that you give the name of the group, then it loads character tables from some database. But those databases, they're for obvious reasons, they're only for simple groups.
Ah, I see.
So. So yeah, so you might have, so some people might still have to do some work.
Yeah. So I mean, this might be a motivation to have an AutoBoot too, which would deal with these generalizations.
Further questions, comments? So if not, let's thank Shai again. Thank you, Shai.